Now, another important piece of evidence for the existence of antimatter comes from looking at beta decay in a bit more detail. If you remember from that 5, beta decay involves the production of a fast-moving electron from the nucleus. Looking at a bit more detail, though, what's happening is that a neutron is decaying into a proton and producing an electron at the same time. So the proton replaces the neutron, the electron comes flying out. But if we look at this in a bit more detail, right, so that's how we might have written it in our understanding from before. Neutron goes to proton plus electron. Electric charge is conserved. Total charge at the start and end is 0. And momentum should also be conserved, as we met in the first unit. But if we look at the direction of recoil of the nucleus and the direction that the beta particles fired out in, we find that they're not exactly in opposite direction, and therefore that they don't cancel out. And that would imply that momentum is not conserved. So basically, what is the solution to this? Well, basically, we postulated, we theorised that another particle must be getting produced, which we couldn't easily detect at that time when we were looking at these experiments. And this particle is known as a neutrino. Although we'll see in a wee second, it was actually an antineutrino. And it's got no charge and very small mass, which makes it very difficult to detect. There is, incidentally, but you don't need to know this as part of the course, there is an equivalent producing a positron and a neutrino. But if we write this standard production here for the standard beta decay, then a neutron decays into a proton and an electron and an antineutrino. It's a neutrino symbol with Greek letter mu with a bar above it. And that's the full beta decay. There's incidentally the positron emission, just for completeness, but you don't need to know about that.